Now let's look at second order derivative. So just to remind you what the second order derivative is. Second order derivative is to derive once again over the first order derivative. So it's just to derive 2 times. So here the only thing is we need to separate 2 types. One is the straight or the direct second derivative, which is like the case here. fxx, that means, oh, previously we have f partial on x, which is partial derivative of fxy on x with respect to x. That's this highlighted term in the parenthesis, in the square parenthesis. And then you derive this with respect to x once again. That's why it's f partial on x once, and then partial on x for the second time. Okay, so now let's look at the calculation of it. Example 1b. Okay, so here I'm using the same question from the first one for continuation. So in the first one, fx has been derived as minus 4x plus 3y, and fy, partial on y, has been derived as 3x minus 16y. And here you were asked to derive the second order straight, the direct second order derivative, which is to derive fxx, fyy. So here, that's why I'm recommending people not to panic when it goes to multivariate case. Multivariate case seemingly to be more complicated because there are more variables involved. However, as you're doing partial derivative, you can see the irrelevant term just goes out, right? So here, fx partial on x, that's the second order derivative of second order partial derivative of fx over x, right? So what we do is we are working on f partial on x, and then treating x as the variable to do another partial derivative. So here, f partial on x, right, is minus 4x plus 3y, and then you are doing another partial derivative on x with respect to x, then 3y is considered as a constant, and here you're just doing the derivative of minus 4x. The result is minus 4. Similarly, f partial on y is 3x minus 16y, and fyy, which is a partial derivative of this new function with respect to y, in which you only consider y as the changing variable, x as the constant, then the first term's derivative equals to 0, and the derivative of the second term is minus 16. See, it's getting simpler and simpler as we are doing a higher order derivative. Okay, so that's question 1. Example 2b. So now, previously we had marginal utility of 1 equal to, here, 2x1, x2 to the power of 6, right? And we had marginal utility with respect to x2 as 6, x1 squared, x2 to the power of 5. So now you were asked to do the direct derivative, which is mu11, mu22. Again, what you do is, in this case, you are continuing with mu partial on 1, and you're doing another partial derivative treating x1 as the variable, right? Namely, therefore, 2x2 to the power of 6, that's the constant multiplier to x1. So its derivative is just 2x2 to the power of 6, because x1 here is just a linear form. And the derivative of this linear form is just its slope, which is 2 times of x2 to the power of 6. Now for the second one, marginal utility of partial on x2 twice, right? So now we're working on marginal utility of 2 and still treating x2 as the variable. So 6 times of x1 squared, the entire term is the constant multiplier, 6x1 squared, multiplied by 5 times of x2, 5 minus 1. Again, just to remind you, it is fx equals to k by x to the power of n, f prime x equal to k by n, x to the power of n minus 1. In this case, k is 6x1. Let's write it here. In this case, k is 6 times of x1 squared, n equal to 5, x equals to x2. Right? Then its derivative is k, keep it unchanged, 6x squared, multiplied by n, which is 5, multiplied by x, which is x2 to the power of n minus 1, 5 minus 1. So the result is 6x squared by 5 by x2 to the power of 4, and 6 can multiply to 5 equals to 30 by x1 squared, x2 to the power of 4. So this is a case of direct higher order, which is second order derivatives.